Okej, välkommen alla som är med på vårt nästa webbinar inom projektet Applied AI Digital Innovation Hub North. Det här webbinariet kommer vi att hålla på engelska, så att jag kommer snart att skifta språk till engelska. Men först lite grann om hur det här ser ut idag. Vi kommer att spela in det här webbinariet så att vi har en föreläsning som man kan se på i efterhand också. Och ni som inte vill vara med på något sätt, på så vis syns ni inte. Det är därför vi har mutat och tagit bort kamera. Men frågor och sånt som ni vill ställa, gör det i chatten så ska vi ta upp dem allt eftersom är tanken. Agendan ser ut så här, att jag inleder säga några ord om projektet och sen kommer jag att lämna över ord och bild till Niklas Karvonen på Substorm som pratar om verkliga behov angående dagens tema, om att ha för lite data tillgängligt när man ska använda sig av Applied Artificial Intelligence. Sen kommer Marcus Lewicki och hans forskningsgrupp som idag representeras av Prakash Chandrashippa berätta om vad är state of the art, hur löser man sådana här problem som är ett vardagligt förekommande faktiskt. So by that, I will switch to English and say welcome again to all our listeners and webinar attendees today. This is one of the webinars in a series of several that we will do during the next coming 2 years. This project, Applied AI Digital Innovation Hub North, is a 3-year project that we started a year ago, actually. The region that is the target group, where we find the target group, is Norrbotten and Västerbotten. SMEs are in focus, and the ambition is to become a great applied region regarding artificial intelligence. And here you see actually the web page where you can find all the information that we collect during this phase. And you can also find contact details to all of us if you want to know more or discuss more after this. But please stay also after this event if you have some more questions. The ambition with this project is that we will increase the knowledge about AI in the region within the companies. And we will do that by running a couple of research projects involving companies in the region together with Marcus and his colleagues. We have 3 professors behind all this. Marcus is one of them. We have Anna Stålbröst and George Nikolopoulos in the robotics area that is behind this, and we have selected companies to get involved in these projects based on real needs that we have seen out there in the region. And these projects are up to 1 to 2 years long in time, where we try to solve a real problem. We're not only doing this, we are doing webinars. It's about competence and increase the competence within the region. And this is a typical way to do it during these times. We have a pandemic, so all these kind of contacts we do behind the screen, unfortunately, but one of these days we will be able to meet all of you the normal way, we hope. So by that as an introduction, I will leave the word and the pictures and the screen to Niklas Karvonen, representing Substorm, which is one of these AI companies in the region and that is facing all these problems that we have seen now. And he has a challenge to solve them. So by that, Niklas, you can take it from here. Welcome, everyone.
Thank you, Mikael. Like I said, like Mikael said, my name is Niklas Karvonen. I am the CTO of the Substorm. I have a PhD in distributed computer systems from LTU. I've been a programmer since somewhere early mid-90s. And I've also been an entrepreneur for more than 15 years now. And just shortly a little bit about Substorm. We 2019 in September, Tromb decided to create a new company called Substorm that would sort of, whereas their normal digital business development within these fields, and they sort of saw that a new field is emerging that they want to tap into. So instead of making Tromb even bigger and adding more things into Tromb, we broke out and created Substorm. So quite a young company. Here's some bragging rights. We are in Luleå, Piteå, Skellefteå, Stockholm, Gothenburg now. Especially the middle one here, the 50-50. Well, I would say almost 50-50 because we're actually now 9 men and 8 women, but still pretty good distribution, gender distribution in this company. And like I said, we work together also with Tromb. So together with Tromb, we're more than 60 digital business developers. Here's how the distribution looks across the country. And I think that's this very short introduction to Substorm. And now I will share with you a few of the things that we have seen so far. Like I said, we're quite a young company, but already you can see problems or challenges within this field when it comes to data in the wild. So we will look at some real examples. Although I have changed, it's not the data that you look is made up to sort of to predict our customers. So once when you get to a company, you start working with them. They have lots of data, right? In any kind of systems, databases, and you're always really thrilled to have a look at this and really super psyched to get to start working with this data and see what you can do with it. And then you find things like this. This is what I call the dream order. So if you look at this, it's pretty clear here that someone has put, well, if it's not the dream order, then someone put the customer number where the amount should have been in some system or some file or somewhere. There's no protection for this to happen, no sanity check on the amount. And this, of course, this example is really easy because you can sort of say, okay, mostly they order about 10, 15 of something, and all of a sudden there's almost 1 million. But sometimes if the order, imagine if the order value would be, or the order amount would be similar to the customer number, then it's a much trickier figure. So here in this example, of course, we removed all these lines. So then you lose a little bit of data, 0.5% or so, and then you move on. Then you get this one. So here you typically that you will have missing data. It could be a sensor that's not reporting correctly. It could be that it's a value that you don't have to input into a system or something, things like this. So here we see that variable B actually has much fewer values than the other one. In this particular case, however, this was not the case. So first you say like, okay, should we drop it or should we use any of these methods to sort of fill out the blanks here with some mean value or some other technique? But then you talk to the customer about this, and it turns out that this is a latching value. So what they are only registering the changes here. So when variable B here says 20, it means that it changed for some previous value. And in this case, it was even more tricky because sometimes you would get data sets, like you would get these files where variable B was missing for maybe 6, 7 consecutive files, which meant that you had to go back sometimes years in time because the value hadn't changed. And of course, upon first glance, you assume that, okay, this is a variable that's missing, but it wasn't. But sometimes, of course, you do have these missing values, which then the question comes, should you try to fill it with something and what to fill it with? Or worst case, you have to remove some data. And once again, your data set gets reduced. Another example here. Is this a positive customer behavior change? This question. So you see that customer 52, here the customer ID 52 orders 200 on line row 6. You go down, you find it again, row 12, orders 200, find it again, row 16, orders 200. All of a sudden, and now we're really happy because on row 19, he or she multiplies their usual order by 5. All of a sudden, this one starts ordering the same amounts as these other clients. And the question is then, okay, now we're really happy. The sales team are high-fiving and saying like, great. But then it turns out that this is actually one of the customers left, and they took a new customer in. And someone decided, well, I mean, we have customer numbers that we can reuse. So they reused the customer number 52, and you end up with this. All of a sudden, the behavior of the customer changes. And once again, I mean, imagine you're modeling this with machine learning. So you're looking at the, nobody told you this, so you're looking at the patterns that you can find. And some of the customers are behaving really strangely. All of a sudden, you know, you see big jerks and the models are not performing well. And then you find this problem. And once again, for certain amounts here, it's a matter of being 5 times as big all of a sudden. But this is data that I made up. So maybe now, if this would be a real life scenario, you might not see this big change. You just see a little subtle change in how the customer behaves all of a sudden. And then you ask the company, even if you find it, they might not know what date did they actually perform this switch. Someone just updated some record in a database. So then the question is, can you use number 52 here? Maybe you drop it, and then you're left with even a smaller data set. This is another great one. It's not so much about missing data. It's about if you consider an Excel document, you know, you have it starts with column A, top left, right, and then you have AA, AB, AZ, AD, etc. And then you turn to B, and then you have BA, BB, etc. If you check how long this is, it reaches MC. So this is actually over 300 columns wide. And then it's sparse. So they have some, depending on where people input things, it ends up in different columns. So the data it's like this infinity scattered matrix. And to make things even worse, sometimes there were mixed types in this data. So here it's really challenging how to get this into as some usable data. Have only a few rows that actually has a value in a certain column. So you have to try to see like, okay, is this row matching any other column? So you kind of almost need machine learning even to make a data set out of it. So these are examples that we have seen, and it can get even worse than this. I mean, now the previous examples are, of course, from computer systems. So you get the data from some system. It's already there. It might not be annotated at all the times. And we know that annotating, like hand labeling data, like watching an image and saying, yeah, this is a computer on this image, watching another image, that takes time and effort. And it's always a problem with the machine learning that you try to, nobody wants to sit and hand make these large data sets, thousands of images or texts or whatever it might be. But it gets, sometimes we work with people that have real hardware. So what if I told you, can you tell me the health of the ball bearing inside your car motor? Then someone has to take apart the whole car motor, look at the ball bearing, and it gets even worse because you might have several people doing this. So the question is there subjective interpretation of the ball bearing good enough for this? So that really leaves you to today's topic, which is you have a bunch of data, and it should basically say data work, but you have a lot of data to start with. But once you start sort of looking at this data and what you can do with it, you have to drop something there, you have to filter out something there, and it just gets smaller and smaller and smaller. And worst case, you end up with a few rows in your training example at the end. An extreme example of this is a company that was really happy that they had gigabytes of data that we could look at. And in the end, it turned out that we had less than 1,000 training examples from these gigabytes when we tried to reduce it to the actual problem that they tried to solve. So there's definitely challenges in this field. Companies do have a lot of data today, but it might not be the correct data, and you always find yourself in a shortage of data, I kind of feel. So with that, I will leave over sound and audio.
Thank you, Niklas. So Marcus and Prakash, it's your turn to take over.
Thank you very much. Thank you also for this nice presentation, Niklas. It's very good to see how you highlight several of the problems and you notice them in some of your contacts. And I have a history of like almost 15 years of working together with companies, and it always turns out that the first start, making the data ready for the AI, that's the most difficult one. Yeah, you can change to presentation mode, Prakash.
Yes. So is it just?
Yeah, yes, Prakash has 3 desktops. He has to share the right one. Yeah, you have to swap them and then it will work.
So Marco is fine now?
No, can you share the correct screen, please?
Okay.
Make new share in Zoom, sorry. Yes, perfect. Okay, so I'm Marcus Lewicki and Prakash, we will both speak a bit. I will first give just a short introduction about our group a little and some other problems we are tackling. And then Prakash will dive into the machine learning methods with few data. There are many problems connected to data, also missing data and anomalies, which we say. That's not part of our presentation today. We really want to focus on when we have a few data and it's actually costly to acquire more data and especially more data with ground truth. So I think one of the takeaway messages of today should be that everyone knows what ground truth is. That is the annotation made by users, what we expect the machine learning algorithm to report. But before we dive into that, some general points. As Mike has already highlighted, we are part of this AIDIN project, and we have an even bigger mission of LTU AI to become a sustainable flagship in applied AI on national and European level. And here in the North, we can really drive innovation forward more fast than in other areas. What we do in our group is we do several research areas. That is on fundamental application oriented and application level. And we are here really on the application and application oriented level. We want to do machine learning for the welfare of society. And we have some of the areas where we are more strong in and have some ongoing projects. Some examples are, for example, the Space Data Lab. Maybe you heard it. 2 weeks ago, there was a launch, last week, the launch of the AI agenda of Sweden. And the Swedish Space Data Lab was highlighted as one of the great examples where satellite data becomes useful for anyone because the intelligent processing is done as services in an open data queue. And there are some examples of projects where satellite data is used for. And there we had similar problems in these examples. First, it sounds like, yeah, you have terabytes of satellite images. But at the end, it turns out the real useful data and the real useful parts are very hard to acquire because you have to find out where is the interesting region. And then you have to also annotate the data, a few images manually. And we want that the manual annotation process is as short as possible and the machine can take over very quickly. We have also some other projects where it's here in the north quite nice about delivery processes. And we are quite strong in chatbots and natural language processing. And there was a previous seminar where we spoke about that. We also do industrial application projects like here, where we want to analyze parts of vehicles. And that's again a quite interesting project. The machine learning algorithms which we had used just a few data, and even not real data. It was not images from real tractors, but just model trucks in a lab. And the machines could still generalize well enough to, I mean, the learning machines could generalize well enough to work in the real world as well. And what's quite interesting, maybe for some of you in the audience, we do quite a lot of teaching, and we don't only have programs, but we have courses which are open to anyone. And one of the highlights is the Introduction to AI course, where we have like typically every half year around 500 participants joining this course. Yes, this year is the start of the first 5-year Applied AI Civil Engineer program. It is a kind of bachelor master program starting in Hösten, autumn, yeah. Towards gender equality, we also are almost gender equal. With the new hirings, at least, we always have like a 50-50 ratio. There are some old members we took over, and then the ratio is a bit higher towards men. But for the machine learning group, it's also quite remarkable. So we are really looking in the gender aspect, and just yesterday we hired 2 postdocs, a male and a female. So we are getting the tendency better towards gender equality. Now I will hand over to Prakash, who will really focus now on the problems with few data. Please.
Yeah, thank you, Marcus. Yeah, and yes, hello everyone. I'm Prakash, and today I'll be talking about some machine learning methods which we can use about using the few data. And when we say about the few data, it's like how to utilize few labeled data, although when we have a lot of unlabeled data. So that will be our focus. So the outline of this presentation would be, we'll be talking the introduction and what is the real motivation, which is about then what should be the goal for achieving the machine learning using the few data. And there are some concept about the priors, what are the current approaches we're talking about, which include supervised, unsupervised, and then self-supervised methods, which is our focus. And then we'll get into the contrastive learning. One of the method from representation learning is self-supervised method, and talking deep about how contrastive learning works, how it could be utilized, and some remarks, and the end we'll have some open research questions on that part. Okay, so when it comes to the research in interest about about this topic, so the very foremost important question is come that how can we reduce the requirement of labeled data in when we supervising the machine learning method. And one can easily connect it, because we do understand that labeled data is mostly related to the human efforts, manual. It is a time taking, it costs a lot of money. This is for sure that when it comes to the real applied AI objectives in the industrial aspects also, so we have a lot of data, but quite less data is available when it comes to labeled part, because again it's like a human efforts intensive part. So the whole motivation problem statement is about how can we reduce the requirement of labeled data while using raw data available. So when I say raw data, it means data is generated being a part of the process of the business, industrial aspect, but it is not labeled. So how can we leverage that part? That was like one of the interesting aspect of this. Then it comes to that what we're talking about is that we want to learn using few labeled data, but and also want to utilize the unlabeled raw data, but how it should be. So this is like we can say our goal actually. So in the left side of the diagram, we could understand that we have data, equally we have labels. That is a perfect picture for supervised scenarios for the learning purpose. But what we wanted to achieve is that we have a lot of data, but a few labels, and all other data is in just unlabeled part. So this is like, if we can achieve that in machine learning, that could be the ideal situations we have. But in the reality, when it comes, then this is not just the details, but if we want to reduce the requirement of labeled data, we want to reduce the intervention of human efforts manually in labeling the data, then it comes on the cost of the priors. And when we talk about the priors, it's about the human intelligence we put to with the machine learning model, so we can reduce the requirement of the labels. So we can see that if we have sufficient labeled data in supervised problem, we do not require much priors in terms of it could be network selections, parameter tuning, it could be feature engineering. So we do not require much, and state of arts are available, we can really use it in the applications. But on the right side of this diagram, we could understand one who wants to reduce the requirement of the labels, then definitely it comes on the cost of the priors. So that priors can be thought of in terms of knowledge, it can be terms of the intelligence we can understand. So and bit more we can understand in the next slide. So the whole focus is here that we want to focus on the prior part. So how to achieve that, how to obtain that priors in terms of knowledge, in terms of experience, that we could utilize and reduce the requirement for the machine learning. Okay, so just for a very simple explanation about what can be a prior. So in general, that prior we can think of in terms of experience, and I believe that most of the people are like pretty much aware about that we use transfer learning. So when it comes to the transfer learning, it's about like we utilized the model which is already trained on some other data, and we wanted to fine tune it on the data we have on the problem statement we want to achieve. So that we can see that model comes with a knowledge, a basic knowledge about the data and it's a domain, and we wanted to use that experience and knowledge. So, and the other aspect of the prior could be that human reasoning. So being a intellectual, we apply our human reasoning, understand the relation between the data inputs, identify new features, understand the correlations, and once we have all this, then we try to incorporate in the machine learning process. So again, this is another type of the prior. So although prior is not just limited in terms of experience and knowledge, but in general, that could be a starting point to think about how prior can be used in this particular scenario when we are interested to learn with fewer data. Now, coming to the current approaches. So in the current approaches, end-to-end learning is one of the domain, and where like transfer learning comes into the picture. I must say this is well-known, popular, and a successful approach where like models are trained on different data. I mean, and we just fine tune the model based on the new data set, based on the business and research problem we wanted to solve. So transfer learning is quite a popular, and we use it, although there are some limitations also it comes, and that we will discuss little later. In another part of the end-to-end learning is that, so it is about the clustering part. So we don't need labels. We have a lot of data and we apply different clustering algorithms to group the data, based on their characteristics and different properties. So those are like end-to-end learning, which is quite popular also. And now we come to the main focus about the representation learning. So in representation learning also, I'll talk about a specific method which comes into the category of self-supervision. It's a contrastive learning. So contrastive learning is, and before getting into it, I just wanted to take something out of the motivation that why we are focusing it here. Reason being an applied AI, and we are talking here about the industrial revolution using applied AI. Then, as I discussed earlier, and then Marcus also included that in the presentation, that we have a data, but most of the data is not labeled, but we have unlabeled data. So there should be some mechanism which could learn based in fewer labeled data, but utilizing application specific unlabeled data. So if that can be done, then it is a big motivation for applied AI in industrial sense to go ahead and apply for it. So this is the reason we are focusing today here on the contrastive learning part. Okay, and just in a brief explanation, so we can understand the differences in terms of like what it offers and how it could be limiting. So transfer learning, as we know that it is a supervised method. So the process of supervised method is like there's a model which is get trained on a specific domain A data, and we utilize that model fine tune on the domain B data. This is how this is like supervised transfer learning works. And there are a lot of evidence that I need not to even mention that transfer learning shown a very good results in terms of higher performance, in terms of like lesser training time. Both the aspect we can understand. There are a lot of examples that, but and coming to the like some of the limitation part which we need to understand, that it really happens. Actually, it is very good for the initial layer, low level features actually. Just for the example, if we are working on images of animals, okay, so and that model is being trained on the images of animals, and you wanted to use this particular model for identifying different cars and vehicles. So the point comes that the pre-trained model, as in a transfer learning we wanted to use, so one can understand that initial layers having common image low level features, which is very much useful for across all the application. But we need to focus that this model is only as good as for the initial layer features. If we talk about the further layers in more complex features we wanted to learn, then those become very much application specific. It means that the model can be fine-tuned, but it is not leveraging the complete, I must say, the complete capability of the learning. So this is like, and there is no scope for utilizing unlabeled data. So just to keep in mind that using transfer learning is quite successful, but it has its own limitations. And the limitation in perspective of what we are talking about, utilizing application-specific unlabeled data. Then come to the clustering part. It's nowhere like any unknown concept. Most of the people are known about it. So no labels here. So we cluster. There are different clustering algorithms, and in computer vision also many networks are available to get the features and cluster it. So so nowhere it's like people are using it, and there are many state of arts. But when it comes to this kind of method, although it is an unsupervised method, but one of the important aspect we need to understand, it is really very compute intensive, because image data itself has its own complexity in terms of computation part. And when we try to connect this aspect with applied AI sense, with industrial part, then it becomes very important that we do not just get the result, but we get it efficiently, less computing aspect. So this is like the remarks on the unsupervised learning, and then we get into the focus part is like contrastive learning. So before understanding it, we can understand so far that we have gone through the transfer learning, which was a fully supervised scenario. Then we talk about clustering, which is unsupervised scenario. In supervised, we were completely dependent upon the labeled data 100%. Second, we are talking about unsupervised learning, where we were not dependent upon the labels, but it has its own limitation in terms of computing, in terms of utilization of application specific data. Now, when we come to the contrastive learning part, this is like self-supervised method. So self-supervised method is that it allows models to learn the presentations from unlabeled data. And when I'm talking about the unlabeled data, it is like an application specific unlabeled data. So for example, one wants to learn about a different vehicle recognition or vehicle classification problem. So we can understand that we might have only 5% or even 1% of labeled data, but we have a lot of images as a part of the process. How do we utilize it? So contrastive learning is basically a pre-training concept. It means before doing actual learning, actual training of the model on labeled data, how to prepare your model to get ready for that learning. So it can learn very fast, very efficiently with less number of labeled example. This is the main job of this self-supervised based contrastive learning actually. And how it works in a pretty simple way. It learns the similarity between augmented representation of the same image, and it learns dissimilarity in otherwise. So we will try to look at this part as an example. See, we can see here like two different images. One is a chair and the other is the dog here. So now we could see that these are their augmented representations. And for a specific example, I might say it is a random cropping, right? So we just use the random cropping and produce the augmented representations of the images. Now what happened? We utilized here CNN architectures. It could be CNN architecture which we supposed to use for the actual learning task. So one should not get confused that there are no 4 CNN. It is the representation that the very same network consumes the augmented representation of the input images. So augmentation representation from same image is like we can call it like homogeneous. And the otherwise scenario can be heterogeneous scenarios. Sorry. Yeah. Then there are MLP heads. It's multi-layer perceptrons. The role of this small neural network is to learn the similarity between the augmented images from the same input source and learn dissimilarity across the augmented representation of different images. So the role of this MLP here is to understand this particular scenario, so it can minimize the distance between the augmented images representation and maximize the otherwise scenarios. So this we could understand like that. It is pretty simple that for the very same augmented representation, it try to attract, and in the otherwise scenario, if augmented representation of a dog on the left side goes with the augmented representation right side from the chair, then it's going to repel and going to learn the dissimilarity. So one very much important observation and a take-home lesson is that in this whole process, we do not require any labels. Although this is application specific data, but it does not require the labels. So by doing so, we are pre-training our models in order to make it ready for the actual fine-tuned supervised training with fewer data sets. And what will be the advantage of doing it? By doing so, network will be very much ready and it will be quickly able to learn the the supervised learning seen in very less data and very much efficiency. So this is like how whole process worked, and we quickly talk about the state of arts in this method. This particular branch of machine learning is like very much quickly evolving these days. In 2020 itself, we could see there has been a lot of state of arts published during different conferences, and some of like one is like SimCLR. And I will not get into the more detail about it, but just like I'll try to cover it in a very brief way. That SimCLR, it's talk about contrastive learning scenario where positive and negative examples. When I say positive, it's like augmented representation from the same image, and when I say negative, otherwise scenarios. So it utilizes both the combination in the pre-training part. This is how it works. And when it comes to momentum contrasting learning, the other way of achieving the contrastive learning, which does not use negative examples in the training, but it uses momentum encoders instead. And the third, which talks about how along with the contrastive learning to achieve the very same result. So this is like a very brief idea, what are the state of arts established in this particular field so far. A very quick understanding about the comparative summary on state of arts. So before understanding it, one should very right side that this is it's a gray pillar. It's talk about the supervised performance on ImageNet, and all these methods which are benchmarked here are ResNet 50 architecture. And now on the left side, we can see a lot of orange, green, and blue bars. These all mostly belongs to the contrastive learning with the different combination of the methods. And one should understand that all the methods of contrastive learning clusterings are using only 10% of the labeled data. It could be even less, but for the comparative purpose, I just wanted to make sure that it just uses the 10% data, whereas the supervised method is using 100% labeled of the ImageNet. And when it comes to the performance comparison, we can understand that using this, even using 10% of the data itself, we are mostly able to achieve very same performance using contrastive learning. So here some of important remarks we should understand, that as learning method is important, but the very same time these priors are becoming also very much important for us. So how well we can design the prior using the domain knowledge, using the data analysis, and using some business knowledge, how do we can utilize these priors in the method? This is very much crucial, and it can achieve even the better results. And secondly, that we are able to achieve the results even with the 10% of the data, which shows the possibility that in the applied AI sense, it opens up a lot of opportunity where data is being produced every single day, but it is not labeled as efficiently as it can be. So there, such kind of scenario, contrastive learning can be a very much method and very much good candidate to apply and obtain the AI solutions. This is a much detailed comparative summary about the methods being used. So I will not get into the much detail, but it can be referred a little later also. That it basically talks about all established state of art, mostly from 2020 last year, and what are their key factors, how they contribute, and what are their limitations. Because to apply such methods, it required to understand what we can offer to those methods in terms of data, in terms of scale, in terms of computation, basically. So the limitations also very much important here. So this can be even referred later. And then there are some remarks on the contrastive learning. Yes, contrastive learning is leading in the self-supervision. and it shows its potential, as we could see that even using 10% data, and there are scenarios then like people are just using 1% of data to achieve quite acceptable performance. And when it comes to some kind of limitations for the contrastive learning, so it is also a compute intensive, and specifically I should mention this note for the state of art from SimCLR, which uses negative pairs, because one can understand that if we are just comparing two images, every image has 3 augmented representation, then we can understand the combination it makes for the negative in comparison to the positive pairs. So this is like one of the challenge in the contrastive learning, which has its own research potential to solve for application specific requirement. Then augmentations play a crucial role, which so it required a knowledge, it required an empirical study to perform the contrastive learning based learning. And yes, it uses application specific data, unlabeled data, which is the main motivation for us. And the final remarks is about CL can be a benchmarking framework, so it is like set of different methods for different sort of domain applications to apply. So in the future, we can look forward to have such kind of benchmarking framework, which can be directly applicable for the industrial AI purpose. And finally, I will drop here for some very simple research questions here, that how do we devise computationally optimize contrastive learning for application specific context, considering semi-supervised scenarios? In more simple words, that we are here talking about how do we make a contrastive learning candidate for a business. It could be like space data, it could be data from agriculture part. So application specific context, can we derive contrastive learning method which really fits into the semi-supervised scenario where most of the data is unlabeled, but some of the labeled data is available? So that shows like a open research questions here. And the next question is talking about how do we incorporate it, because incorporation it in the pipeline is again, as I talked earlier, it is compute intensive. So how do we eliminate that part? How do we reduce that part? That can be a very interesting research questions. So that's all from my side, and I would love to have like questions from audience on that. Yeah. Thank you.
Thanks a lot, Prakash. Very good presentation. Marcus and all, some questions. It's time for that now, and I see that Marcus put a link in the chat where you can download the slides from today's presentation if you want to know more.